In this video, I'm going to be talking about capacitors wired up in a series circuit and parallel circuit. In these two different problems, we're going to take a look at the Q value, the charge, the total capacitance, and the voltage. So let's take a look at our series circuit over here. And we're going to start off with finding the total capacitance. So the rule for finding the total capacitance is you have to add up the inverses, and that's equal to the inverse of the total capacitance. So we're going to take 1 over 5 microfarads plus 1 over 10 microfarads, and that's equal to 1 over the total capacitance, or the equivalent capacitance. So if we take 1 over 5 plus 1 over 10, we get 3 over 10 equals 1 over CT. And I dropped that unit of microfarads, but I'm going to bring that back a little bit later at the end. And I can go ahead and do a cross multiply. And I'm going to end up with a value of 10 over 3, or if you want to round that off, 3.33 microfarads. Now we're going to use this formula in a few different ways to get the rest of our answers. So we have our individual capacitance for each one of those capacitors. Now we have the total. Go ahead and box that up. And now we're going to go ahead and find the individual voltage drops of each of the capacitors. So because it's a series circuit and all of the electrons are flowing in a single loop, there is the same current everywhere. Okay, so I is current, so it's the same current everywhere throughout the circuit. Therefore, there's the same Q value for each of our capacitors. So if we go ahead and find that Q value with our total capacitance and our total voltage, then we can go ahead and use that Q value for both of our capacitors. So if we have Q, and I'll put QT for total, equals the total capacitance of 3.33, and I'm going to put times 10 to the negative 6th farads because it's micro. And then I'm going to go ahead and multiply that by our total of 40 volts, which is in our original picture. And that would give us a total Q value of 1.33 times 10 to the negative 4 coulombs. Okay, now that Q value applies to both of our individual capacitors. So I can go ahead and use that number twice. Now, if I go ahead and take this formula over here, Q equals CV, and rearrange it, it's V equals Q over C. So if I want to find my individual voltage drops, all I have to do is put the Q value up top right here as my numerator and divide it by my individual capacitance. So I can multiply it, or divide it by the 5 microfarads and the 10 microfarads to get my individual voltage drops. So let's go ahead and do that. All right, so I went ahead and divided my Q value by the capacitance of each one of my individual capacitors, and I got a voltage of 26.6 volts for V1, which is this first one over here. And then I got a voltage drop of 13.3 volts for this one over here. And that should equal 40. If you add those up, it actually comes out to 39.9, only because I did a little bit of rounding. If you want to be a little bit more exact, you could have left some fractions, and these numbers would have been slightly more exact. All right, now for our second one, we have a similar scenario, but we have a different set of rules. Now, if you want to find the total capacitance, that is just simply the sum of each of your individual capacitors. Now from there, we have a different set of rules for this one. In a parallel circuit, each of the different capacitors gets the full 20 volt voltage drop, unlike our series circuit. In our series circuit, because there's a single loop, it basically has to conserve a little bit of that voltage, and it drops a portion of that 40 here and over here. Since the electrons only go through one of these loops, they either go through this first loop over here or the second loop over here. They're able to drop that full 20 volts through each of those different branches. So for this one, we don't have to solve for a voltage value. We're going to work our way in the other direction, and we're going to find our Q values. So we're going to go ahead and use Q equals C times V, and then go ahead and solve for our Q value for each of those capacitors. All right, so I found my Q value, my Q1, which is my charge for my first capacitor, and my Q2, which is my charge for my second one. I got 0.002 coulombs and 0.006 coulombs. And the final thing I can go ahead and solve for is I can go ahead and solve for my total Q value, which is just summing up my two values of 0.002 coulombs plus that 0.006 coulombs, and my total Q value is going to be 0.008 coulombs. Okay, so for these two problems, there's a different set of rules. Neither one was very complex, but there's definitely a different set of rules for each one of them that you have to be familiar with in order to solve for your Q, C, and V values. And if you had to solve for something like the potential energy, you can go ahead and use 1/2 CV squared for the circuit as a whole or any of the individual capacitors, and you can go ahead and find the potential energy for any of the individual capacitor or the entire circuit as a whole. I hope that was helpful in helping you solve for different Q, C, and V values. Thank you for watching and listening.